Hello, everyone, and good afternoon. Welcome to our Science Speaker Series event that is both hosted by the Department of Physics and Astronomy and by the College of Arts and Science. Today, we have an extremely awesome presentation coming in with brand new results using JWST, or the James Webb Space Telescope, or the Just Wonderful Space Telescope, depending on how you want to name it today. Giving the talk today is Ryan Lau. He is an assistant astronomer down at NOIRLab, the National Observatories in Tucson. Prior to this, Ryan did his PhD work at Cornell and then had a postdoc appointment at Caltech and then over at the Japanese space agency JAXA for several years before he moved down into Tucson. And as you can see with the picture on the slide, we're going to be talking about some really cool stuff with JWST, and I hope you enjoy the talk. And there will be questions and answers afterwards, so feel free to stick around and ask whatever you have. And thank you again for coming up today, Ryan.
Can you guys hear me okay? Okay, yeah, I think this works. Awesome. Thanks so much, Noel, for the introduction, and thanks everyone for attending this talk here. I think, this is my second formal talk in like 2 years, so since the pandemic. So it's, again, a little nervous, but it's nice to be back and to actually talk in front of people. Okay, so like Noel mentioned, I'm going to be talking about some of these observations that we took with JWST just a couple months ago. So like this image that you see here. And the focus of my talk is going to be about tracing stellar explosions and cosmic dust. So I'd like to start off with an outline. So for this talk, there's essentially 3 main sections of this talk. First, I'll go through the background, the motivation of this science, and why it's an interesting question and why it interests me in particular. And so this research focuses on revisiting the life cycle of stars and dust, stellar explosions, and also what the origins of dust are, which is a really important question for understanding kind of our own cosmic origins. Then I'll talk about the specific research project that I've been working on, which is studying the origins of dust in the ISM, specifically focusing on these Wolf-Rayet stars and revisiting their impacts on mass loss and dust production. And then this is the part where I'll show some of these early science results with JWST. The paper that we published focused directly on this point here. And then at the end, the last section that I have will be about the kind of the future of infrared astronomy, which is the field that I work in, and also time domain astronomy, which is kind of studying exploding things in the sky and seeing things that change in space. And that will really be revolutionized by this upcoming observatory, ground-based observatory, the Vera C Rubin Observatory. So I'll talk about the synergies between JWST and Rubin and what it means for the future of time domain astronomy. All right, so I really like this picture here. It does a really nice job at summarizing this story of how stars form, how they evolve, and how they die. So I'll walk through this, and then I'll point out one critical issue with this. So to start off, everything kind of begins in this giant, dusty, gaseous star-forming region. You have these giant molecular clouds of gas and dust, and through some kind of gravitational perturbation, whether it's a collision with another cloud or a shock from a supernova sweeping through it, it causes this gravitational instabilities, and so you get this gas and dust in this cloud that collapses and forms these dense cores. And so depending on the mass that falls into these cores, you can either follow this sun-like star track here on the left or this more massive star track on the right. And so it's the mass of this core that will determine the evolution of the star. And so that's a key thing about understanding stellar evolution. So for the sun-like stars, they start off on what's called the main sequence, where they burn hydrogen in their core. And when they do this, they evolve on timescales of billions of years. So that's like a similar evolutionary track as our sun. And then towards the end of this main sequence phase, when it runs out of hydrogen in the core of the star, it starts burning hydrogen on the outer parts of the star, in the envelope or the shell. And then it kind of puffs up into this red giant. And then eventually, towards the end of its life, it'll blow off this material from the outer layers of the star, and then leaving behind this white dwarf, this compact object of this enriched material that's been enriched throughout the entire billions of years of the star's life. And then this material around the planetary nebula will inject into the interstellar medium. That's the material where all stars and planets are formed from, and recycled back into forming new generations of stars. So that's the sun-like star track. I'm a little more interested in the massive stars. These tend to live much more intense lives. So the more massive your star is, the brighter it will be, and the hotter it will be, and also the shorter the lifetime will be. So as opposed to the billions of years of a sun-like star, these more massive stars, like 10 times the mass of our sun, will live on timescales of millions of years, so much, much shorter than these sun-like stars here. So they start their lives, again, burning hydrogen in their core. You can see these stars are bluer because they're hotter. And at the end of their main sequence phase, when they run out of hydrogen in their core, they burn hydrogen in their shells. And I guess instead of a red giant, they puff up into a red supergiant because they're much larger in size than these red giants. And then towards the end of their lives, or at the end of their lives, they can explode as these violent supernova eruptions, just ejecting their enriched innards all over into the interstellar medium, and then leaving behind this dense inert core, either a neutron star or black hole, depending on how much stuff has fallen back onto the core after it exploded. Okay, so that's the overall picture of this life cycle of stars and dust. It does, like I said, it does a really nice job at summarizing it, and it's kind of a pretty picture too. But the one main issue about this is that we now know that most massive stars, oops, let me go back here. Most massive stars will have a close binary companion, and this is a big deal because, as I mentioned, it's the mass of the star that dictates its evolutionary track. So if you have a star that's close enough to interact with the other star, it's going to cause some crazy stuff to happen. So if you're exchanging mass between the companions, you're not necessarily just going to follow one single evolutionary track. And so instead of this picture here, you get something a little more complicated, especially when the star leaves the main sequence and starts puffing up. So for example, when it leaves the main sequence and starts kind of getting larger, it can fill its Roche lobe, which means that it can start dumping material from its outer envelope onto the companion star here. So you can get this direct mass exchange from the envelope of the primary star to its companion. Or if the companion star is close enough, the main star, the primary, could just completely swallow up that companion star, and you get what's called a common envelope, this kind of stellar envelope that's shared by these two stars now. And then from there, depending on how these stars interact, you can either get a merger between those two stars, or you can end up with a detached system that then evolves in other different sequences here. Or, of course, this is still a viable track here too, if the two stars are separated by far enough separations that they kind of just go about their lives evolving as being effectively single stars. So this is what's kind of a major shift in our understanding of stellar evolution. It's not quite this clear single track anymore. There's much more complicated branches of stellar evolution because of the binary companion. And so because of that influence, and because it's a little more complicated than when we first thought, that also complicates how stars lose mass, how they explode, and also how they die. So the common types of stellar explosions that are known are supernovae and novae. These have been known for many, many years. And what I'm showing here is just a light curve, which is the brightness in the infrared of these objects as a function of time here. So days is on the x-axis, and brightness is on the y-axis. So this was kind of our understanding of things that explode in the sky up until like maybe tens of years ago. When we see these emerging classes of red or infrared luminous transients that have been discovered. For example, we know that stars can merge. We've seen the signatures of a stellar merger, which is quite amazing. And so there are these objects that produce these dusty ejecta, these envelopes that appear very red and luminous at infrared wavelengths. These are called luminous red novae, or stellar mergers. We know there are these phases of an massive evolved star where you have this kind of battle between radiation pressure or light and gravity. And in some of these stars, this radiation pressure is winning that battle, and it create these giant ejections of material, kind of exploding lots of stuff off of the envelope of the star that kind of look like supernovae but aren't quite supernovae. And so these have been coined as supernova imposters, so these kinds of giant eruptions from massive evolved stars. There are these Wolf-Rayet outbursts, which is what I'll talk about mainly in this talk. And this is when you can get some kind of dust production event due to the interaction of two winds from a binary star. And so this is an image of a really nice Wolf-Rayet star here that has produced dust in this kind of elegant arc. All right, and I think probably the most exciting thing that's been discovered in the past 10 years has been these neutron star mergers, these kilonovae, these counterparts of gravitational waves of neutron star mergers. And we now know that these objects actually appear to be quite red at late times. So here was this science release from NOIRLab back in 2017 when this crazy event happened. LIGO Virgo detected the signatures of a gravitational wave merger, or a neutron star merger from the gravitational waves. And then it was followed up, and the electromagnetic signature of this was detected. And at late times, that electromagnetic signature appeared quite red and also luminous in the infrared. So this was pretty cool. It's red enough, so this is showing the light curve of this particular kilonova here, that it was detected by the Spitzer Space Telescope. And so the Spitzer Space Telescope was the most sensitive infrared telescope that we had before it kind of got decommissioned. Now we have JWST. But with Spitzer, it was able to detect the 4.5 micron, which is kind of in the mid-infrared range here. So there's the signatures of that gravitational wave, the neutron star merger at 43 days and 74 days after that merger occurred. So I also want to point out that this telescope, this kind of relatively small telescope that was in space, did a lot of work in kind of pioneering this study of infrared time domain astronomy, looking at these explosions in the infrared sky. And part of this or a lot of this effort was pushed by this project called the Spitzer Intensive Infrared Transient Survey, led by Mansi Kaziwala at Caltech. So this is a group that I was a part of a couple of years ago. All right, so let's go back to this picture here. So there's 2 points that I want to make about this, now that we kind of have a better idea of what's going on and what this picture means. So first, this infrared time domain astronomy has really opened up this new window to investigating the lives and deaths of these massive stars. So infrared is a really key wavelength for this because at infrared wavelengths, it penetrates through gas and dust in the interstellar medium and also this material around these stars. So you can see this kind of hidden physics of what's going on around these sources. And the other thing that I wanted to point out, so I've talked about dust a lot, especially in my title slide. I mentioned dust. In the outline, I mentioned dust. It's a super important component in the interstellar medium. Stars and planets form from giant clouds of dust. As they evolve, they can produce dust, and as they die, they also form large quantities of dust. But the actual origin of dust itself is this really huge mystery, and one of the kind of outstanding questions in astronomy. Now, this is exacerbated by the fact that we have these galaxies that are less than 1 billion years old after the Big Bang that have a lot of dust. So for example, this one here that was found by the ALMA array of telescopes, it has the same amount of dust as our own Milky Way galaxy, but it's only 1 billion years, it's less than 1 billion years old. So much less evolved than our own galaxy, but it still has enriched with all this dusty material. So that's kind of an issue because we don't really have an answer as to what exactly is the source of this dust that produces it on such rapid timescales. But one thing that we can be relatively sure of is that they must be from massive stars. So massive stars evolve very quickly on timescales of millions of years. And so they are most likely enriching the dust content of these galaxies at early times. The leading hypothesis is supernovae. Since they're pretty common types of explosions from massive stars, they're ejecting all of this enriched metals that the star has enriched over its lifetime into the interstellar medium. So it makes sense that that's one of the leading sources, or thought to be the leading sources of dust. But the problem with that is that they can also destroy a lot of dust too, and it's unclear how much dust actually forms in a supernova. So this is a major question, but will also be addressed by observations with JWST. So it's a really exciting time for this field. Okay, so basically to summarize kind of the focus of my work and what I'm interested in doing and how I do it, it's tying these two themes together that are intrinsically related, stellar evolution and also the origin and formation of dust. And to connect these two themes and to push our understanding of these themes forward, I use observatories like Spitzer, the Gemini telescopes, JWST, and in the future, I'm very interested in using the Vera C Rubin Observatory to do this amazing time domain observations, which will be conducted from Chile. Okay, and these are the objects that I'm interested in, so some of the ones that I showed in the couple slides ago in the light curve. So these Wolf-Rayet outbursts, supernova imposters, stellar mergers, and also neutron star mergers. But the one that I'm going to talk about mainly today is going to be these Wolf-Rayet outbursts here. So let's talk about this a little bit more. All right, so what exactly is a Wolf-Rayet star? How do you form a Wolf-Rayet star? And how do these Wolf-Rayet stars form dust? So let's start off kind of back in that same story of a massive star that forms. So this is kind of the basic picture of what you'd expect for a massive star. So this big M, let's say that this is the more massive star. We can give it mass if we want, so this could be 25 times the mass of the sun. And then this little m will be the lower mass star. So let's say that's 20 times the mass of the sun. And we now know that most massive stars, the more mass you have, the more rapidly your star will evolve. So the first star to leave the main sequence, to run out of hydrogen in the core, will be this one here. And when that happens, it'll puff up. And what can happen is this kind of mass transfer from the more massive star to the lower mass star like this. And this, it's not necessarily a clean process. It's not just mass is transferred neatly from one star to the other, but you can get this sloppy mass transfer where the material kind of spews out along the orbital plane of the system. What's pretty cool about this is this is very rare, or it's hard to catch this in action because of how short the timescales are for this particular phase. So, massive stars live around millions of years. This phase is probably on the order of tens of thousands of years. But this is an observation by the Hubble Space Telescope that's where we think that we're capturing this particular phase of massive stars evolution. So we're looking at material that's being spewed out along the orbital plane of probably a binary system for one star that's dumping material on the other one. And again, it's not a clean process, and so that's why there's all this messy material being spewed out from it. You can't actually see the binary star here, so that's complicated because of all this gaseous and dusty material in the core here. But with infrared survey, the Palomar-Gattini IR telescope, we have these near-infrared light curves that show this sinusoidal pattern that tell us that more likely than not, there's some kind of binary orbital motion that's regulating this infrared emission here. And so that provides us with more evidence that this is what we're seeing. There is some binary here where the envelope is being stripped and blasted out. All right, so what happens then after this phase? And what we're left with is what we call a Wolf-Rayet star, or a star has entered its Wolf-Rayet phase. And this is the primary star over here that's now in this, that's now a Wolf-Rayet star. And it's kind of this exposed helium core. All of this hot material that's been enriched in the innards of the star has now been exposed after the outer envelope has been ejected or transferred to the companion star. And so because we're looking at this kind of descendant hot enriched material from this more massive star, it's characterized by very extreme properties. It's over 10 to the 5 times the luminosity of the sun, so they're extremely bright. They're very hot, over 40,000 Kelvin. They have very strong winds, which is this material that's being blasted off the surface or in the photosphere of these stars. And they also have high mass loss rates, so there's lots of that material that's being blasted away. So very extreme types of stars. And the weird thing about these sources, despite how intense and hostile their environment is, you can actually get dust formation around these Wolf-Rayet stars. And so that's super weird because dust doesn't just form around hot stuff. You typically need some cool environment to form dust. It's like expecting like ice to form in an oven or something like that. And so it's a big question there was a big question as to how you get dust formation around this really hostile environment. And the answer to that seems to be the presence of a binary companion, as this image shows here. So the key to enabling dust formation, at least around these carbon-rich Wolf-Rayet binaries or WC binaries, seems to be the presence of a companion star, so typically an O or a B type star, which is the more massive types of stars that form. And what happens is when the two winds from the stars interact, you get this wind interaction region here. So in this illustration, you see this dense layer of material between these two winds that are forming that are ejected from these two stars. And in this layer, you can get the right densities, and then downstream, you get the right temperatures to form dust. So this wind collision or colliding wind mechanism seems to be the key in enabling dust production around the Wolf-Rayet star. All right, so since the two stars, they're not stationary, and they can be fairly close, we see them orbit each other on like relatively short timescales on the order of years for some systems. And what that means is, as you can see in this illustration here, since the dust is constantly forming behind the companion star, which, if you think about it, which star has the stronger winds? It's going to be the Wolf-Rayet star most of the time. And then the Wolf-Rayet star is going to be blasting the winds from the O star, from the Wolf-Rayet star to the O star's direction. So you get something like this dusty stream that forms around the O star as the two stars orbit each other. So in this graphic here, it's kind of modeling or showing a circular orbit, or for the dust nebula for a circular orbit. And then for that, you'd expect to see this circular pinwheel that's traced out like this. And so the morphology of that pinwheel is kind of encodes the properties of the orbit of these two stars, which is kind of cool. So this is just an artist's rendition of this dust formation process, but these are actual observations here. So it's essentially a movie of this dust production that's been caught around this system, WR104, over a period of about a year. So we're seeing the full orbital period of this binary system. We can't actually see resolve the binary, but we see the dust forming behind the companion star and then expanding radially outwards after it forms. So this is a little tricky to kind of envision what the dust is doing, because it looks like it's just a spiral stream like moving around. But what we're actually looking at is it's like you're looking at a sprinkler from the top down. You're seeing stuff that's constantly being blasted out from the direction of the Wolf-Rayet star to the O star as it's orbiting. And so the material is actually flowing out this way and not kind of going in this spiral direction here. Okay, so why is this cool? Other than like, yeah, it makes a really awesome movie. Why are these astrophysically interesting objects? And the reason why I find these interesting is because these are descendants of massive stars, meaning they evolve very rapidly. They can produce a lot of dust, meaning they can be these early sources, these dust factories, potentially in the early and local universe, which is one of the things that we're looking for. What are the sources of dust? Well, yeah, what about these things? So in a paper that we published a couple years ago, we looked and did a study of of a sample of carbon-rich Wolf-Rayet stars that form dust in our galaxy. And this is the range of dust, their dust production rates. So they can be pretty prolific dust formers. As a comparison, this number here, this 1.4 times 10 to the minus 5, that's the total dust production rates of these asymptotic giant branch stars in the Large Magellanic Cloud, which is a galaxy close by to us. So the entire population of these stars, AGB stars, which are thought to be a leading source of dust, it's only a factor of 2 or 3 more than a single Wolf-Rayet binary system, so this more massive one here. If you had a couple of these, that means it would dominate the dust production from the entire population of these AGB stars in the LMC. And so that just gives kind of an idea of how important just a couple of these can be in enriching the dust content of their host galaxy. So our method to study this is using this binary population and spectral synthesis code called BPAS to study the dust production from these carbon-rich Wolf-Rayet binaries, red supergiants, asymptotic giant branch stars, and supernovae. So these are other leading sources of dust. So we want to do a more quantitative study to compare the dust production rate from carbon-rich Wolf-Rayet binaries to these other things, to show that we actually know what we're, or to do a more rigorous study of the dust production rate in comparison to these known sources. So this is one of the plots showing the outputs of this binary population synthesis model where we incorporate dust production. So we're essentially looking at a stellar population, a simulated stellar population, that's evolving over this time scale here. So this is in log units. And this on the y-axis is the amount of dust these sources are injecting. So the interesting things that we saw from the models are that these carbon-rich Wolf-Rayet binaries are the first to turn on and form dust, and they also seem to dominate the dust production at least until the asymptotic giant branch stars turn on. The supernovae are a super big question mark because we don't know how much dust they that actually survives their formation. You can get lots of dust destruction, and again, this is going to be a major question that will be addressed in the coming years. So in this, if you had no dust destruction from supernovae, then we could say that, yeah, supernovae are probably the dominant source of dust. But if they destroy lots of dust, then they kind of wipe out all of the stuff that they form. So basically, what we wrapped up, or what we concluded from this study was that these carbon-rich Wolf-Rayet binaries can be an important source of carbon-rich dust at metallicities higher than about half a solar metallicity, which is one of the variables that we investigated this trend for, metallicity of the environment. Okay, so where do we go from here? So this was a couple of years ago. There's still lots of important questions that we wanted to pursue about these Wolf-Rayet stars. They haven't been as well studied, at least in terms of dust production and their dust budget and their dust input into their host galaxies as supernovae or AGB stars. And so there's some important questions to understand if we're pursuing them as serious dust-forming sources. So for example, do we understand the diversity of dust production from these systems? Is it possible to get single Wolf-Rayet stars that form dust? And also kind of a big question about what exactly type of dust do they form. We know they should be carbon-rich, but we don't know exactly what type of carbon-rich dust forms in it, which is an important question to know if these are important sources for dust in the ISM. And to do this, we've been using this slew of ground and space-based telescopes here. Here's a couple of studies that we published in the past year. But the one that I'm going to talk about today is our observations with JWST, the ones I showed in my title slide here, or my title slide. So let's talk a little bit more about JWST first, and early science with JWST. Right, so for those of you who aren't familiar with JWST, this is probably what it looks like floating around at L2 in space. It's a deployable infrared telescope. It has effectively a 6-meter primary mirror. And it's a joint mission between NASA, ESA, and the Canadian Space Agency. So it really was this international, worldwide effort to get this mission going. The telescope itself is cooled passively to cryogenic temperatures below 50 Kelvin by this 5-layer sun shield here. And so that's why maybe during the launch you've heard about how important this was to deploy, because without this, you can't operate at a cool enough temperature to do the science that we wanted to do with JWST. So this had to be deployed perfectly, and it has to always be pointed away from the sun so no sunlight falls onto the primary mirror. So this was a very important aspect of the telescope to kind of keep it literally cool. There is an instrument that's actively cooled. The mid-infrared instrument, or MIRI, is cooled by this closed cycle cryocooler to 6.7 Kelvin. And that's because it operates at the longest wavelengths where you really need to cool down your instrument. Now, the main takeaway point about JWST is that it's the most sensitive infrared observatory between 1 to 28 microns, like almost a factor of 100 more than that Spitzer Space Telescope that I mentioned earlier. So it's really doing some revolutionary science, and it's, we're all pretty excited about what else we're going to be able to learn from its very long mission. So one of the programs that I'm leading for JWST is called this Early Release Science Program. And what this is there's these 13 teams that are selected to do some of the first science with JWST to like show off its capabilities, to demonstrate to the astronomical community what this observatory can do, and to make sure that they understand what's kind of how to maximize the use of it for cycle 2 and beyond. So this kind of rapid education to the community, rapid results to produce, and to show what science it can do. And so I'm leading this team of about 46 astronomers. They're composed of observational astronomers, theorists, instrumentation experts. And so it's been this really awesome international team. We've really ramped up within the past couple of months to get these papers out. So it's been really amazing working with this huge group of people. So most science will take a lot of people and effort to get it done. All right, and then the science that we're focusing on. This is probably my second favorite slide because I spent a lot of time trying to do this animation here, so I might spend some time on it. So we're focusing on the composition and formation of dust. What are the molecular precursors of the dust that forms? What are the spectral signatures of the dust that forms around these carbon-rich Wolf-Rayet stars? We don't quite know that yet because we didn't have the direct detection of it. So that's one of the major questions that we're interested in addressing. And to do that, we're using the MIRI instrument and also this NIRISS instrument. In this talk, I'm mainly going to focus on results from the MIRI instrument. This will be a whole nother talk at a later time in the near future. And then we're also interested in seeing how this dust evolves as it integrates with the interstellar medium. That's also an important question to address to see if it can survive to integrate with the ISM. And for doing this, again, we're using this MRS mode, this spectroscopic mode on the MIRI instrument and the imager of the MIRI instrument. Now, the target that we're looking at is called WR140. It's been dubbed the Rosetta Stone of colliding wind binaries. And that's because it's been super, super well studied for like over the past 50 years. This orbit has been well known. We know the spectral types of these stars. WC7 is the Wolf-Rayet star spectral type. O5 is the companion star's spectral type. We know how far away it is. It's about 1.64 kiloparsecs. So that's relatively close to us. It has an orbital period of about 6.94 years. There's actually much more sig figs in this, so this could go on. Its eccentricity is 0.9, which means that it has kind of an elliptical orbit. So you see here, it's much more elliptical than that circular one that I showed previously, and that affects the morphology of the dust that forms around it. We also know the inclination quite well too, so about 120 degrees. And so because it's this really well-studied, well-understood system that forms dust every time it goes through this red phase or red area here, or periastron passage when the two stars are closest together, we know pretty much, or we knew pretty much exactly what we're going to see to some extent when we're studying this object, or at least what it's going to look like. And so that was one of our motivations of using this as our target for this early release science program with JWST. So this image here is, it's not published yet, but we submitted it to a paper in the Astrophysical Journal. And we took this image, taken at around 12 microns, which is a similar wavelength range to where JWST operates. And this is one of the best images that we had at this wavelength of WR140. So here's where the core of the star is, where the binary is located. And then here is this dust shell that was formed through, during periastron passage in around 2017. So this dust here was about 3 years old when this picture was taken. So I'm going to zoom into this a little bit more because just to emphasize, this image was taken with like one of the best ground-based observatories in the world, the Subaru telescope, on Mauna Kea, which is one of the best sites for astronomy in the world. So you get high up enough where you don't need to deal with the atmosphere too much. That really makes infrared observations difficult. All right, so what we saw with JWST was this. So instead of just this single dust arc, we see more than 17 of these in this evenly spaced sequence of these nested, segmented dust shells. So when we saw this, we were just totally blown away. Like I said, like, oh, we had an idea of what we're going to see, but when we saw this, we were like, okay, this is pretty crazy. But we kind of recognized that the shape of these dust shells here are very similar to the ones that we see in this Subaru image here. So it has this kind of like curved shape here. And that indicated to us it's unlikely that this is some kind of artifact of the telescope that we're looking at, because all of this structure repeats and looks very identical to that one structure that we're familiar with. Of course, we need more proof than that. We can't just be like, oh, it looks right, so that's our paper. We had to be more rigorous about this. So what I'm showing now, these are contours of the point spread function of this particular wavelength at 15 microns here with JWST and the MIRI instrument. So what this is showing is all the stuff that you'd expect to see from a very bright point source or bright central core. So all of these things in white correspond to artifacts from the segmented primary mirror or from the telescope struts. So none of this stuff is astrophysical in origin. This is all just light diffracted and scattered from the telescope. And so what that means is that all the other stuff is real. So this stuff is real. This thing here, which is also looks like it could be a diffraction spike, is also real. It doesn't show up in this point spread function that we see here. So that was crazy, because when things look like this, they're typically an artifact. So that pushed us a little bit more that we really need to understand what we're looking at. When you see new things with new telescopes, you need a good model to understand what you're seeing, or to convince people that we understand what we're seeing. And so that's an important part of doing science, especially with looking at new results. So that's exactly what we did. So there's kind of fortunate coincidental timing that there is another group led by Yinwo Han, who's a grad student at Cambridge University, who was looking at WR140, looking at decades of observations of it with high-resolution ground-based observatories. And what he did is he came up with this geometric model of that dust shell that forms around WR140, and how that evolves over time, over its orbital period of 8 years. So you can kind of see this is a companion star. It whips around and it forms dust in this region here, in the upper right of the orbit, in that red region around the Wolf-Rayet star. And when it does that, it forms this kind of circular, segmented shell-like structure of stuff that then expands outwards. So I asked Yinwo, like, oh, hey, like, these are pretty cool models. What happens if you take them and then you just stack 20 of them together? Like, what do we get? Because that's what we think we're seeing. So he did that, and this was the result of taking those models and stacking them all together. It looks almost exactly the same as our observations, and so we were just totally blown away at how closely the models matched the observations, which seriously, that doesn't typically happen, especially for something new, like new observations with JWST. There's always something that's like wrong that you don't understand. But just that we're able to do this with parameters that we had before our JWST observations, and to match something so closely to our results, it was just, yeah, it was amazing. So we're like, yeah, this is pretty cool. We should publish it. We're pretty sure we know what we're seeing. You can even see this part of the shell here. There's enhanced emission along this region, and we see that exactly in our observations. And this weird kind of spear-like structure, we also, that's what I was mentioning that we thought might have been an artifact, but that's also reproduced by the models because of how the geometry of the shells are stacked together. We see that enhanced emission along that region of dust that's kind of piled up along our line of sight, which is kind of producing this kind of spear-like shape there. So what was pretty cool about this is this also lends itself well to 3D printing. So one project that we've been pursuing with Carol Christian at the Space Telescope Science Institute and Tom Madura at San Jose State University is coming up with 3D prints of these JWST images. So like this one here, this one is really neat because it's actually a 3D kind of tactile print where students or people with blindness and visual impairments can experience the image by just feeling it, and with where the raised intensity corresponds to the level of the of this material that's printed out. Also, we have these 3D printed models of one of the dust shells here, and also where it's not forming dust, which kind of can give you a better idea of what the morphology or the geometry of the dust is. So we're working on this stuff. It's pretty cool. There's a website here, and then also these QR codes. You can access the website for all these 3D printing products. Yep. Okay, so that was just actually half of the paper, half of the science in the paper. I mentioned that spectroscopy was really important for us, and these are the spectroscopic results. And so these don't look like spectra, but what we actually have is spatially resolved spectra. So each of these pixels that we see here correspond to roughly a 5 to 28 micron spectrum that we see here. So this is just a slice of a three-dimensional data cube of spectroscopic information. So each of these pixels we have 5 to 28 micron spectra of, which is exactly what we wanted to get. We wanted to get the direct spectra of this dust here. And so what we saw was pretty much what we were looking for. What are the spectral tracers of the dust that forms in these Wolf-Rayet stars? And we saw these broad infrared bands here that are known as unidentified infrared bands, which is kind of a weird name, but that's kind of stuck with it, or UIR bands. But these features are associated with these carbon-rich aromatic compounds. So kind of these carbon rings in this ring-like structure here that are thought to be polycyclic aromatic hydrocarbons, which are this really important component of the interstellar medium, regulating the energy and the temperature in the ISM, and kind of ubiquitous throughout the interstellar medium. So we see these features in it. We see that dust that forms around this Wolf-Rayet star seems to be surviving out to over 150 years after it forms. And so we've addressed that question of, well, what kind of dust does it produce and can it survive? So the answer seems to be yes, that the dust can survive to integrate with the ISM. And we've identified that the dust seems to be composed of these carbon-rich aromatic compounds. All right, so that was one of our key science goals of our program, to get this spectra of carbon-rich Wolf-Rayet dust. And then also, now that we have this, we can try to look for this in the interstellar medium of other galaxies, which will be really exciting to look for. And so this kind of segues into the last part of my talk, which is to do this, to take what we've learned from this program and then to apply it to all of these other types of explosive infrared luminous transients that we know of, and to really push the science in this era of the Vera C Rubin Observatory and JWST. All right, and the point here is to address this critical question: how do non-supernova stellar explosions contribute to the dust and chemical enrichment of the universe, kind of basing it off of these observations of these Wolf-Rayet stars. I'm going to skip ahead this slide here. And so I'm going to talk a little bit about this and what we need to do this particular study. So one of the critical components to discover these types of transients is going to be some kind of transient discovery engine. And we will have that with the Vera C Rubin Observatory, which will be an 8.4 meter telescope built on Cerro Pachón in Chile. And Rubin is going to take essentially movies of the sky to capture these transient events and to detect them and to let us know where they're occurring and also how bright they are and their evolution, which is critical for following these up and characterizing their dust production and also their spectral signatures. So I guess I'll go through this quick example here of one type of object that we might expect to detect with Rubin, and that could be this stellar merger candidate here. This is an object that we discovered in the SPIRIT survey with the Spitzer Space Telescope. So this is showing the spectral energy distribution, the model of this type of explosion or the stellar merger. So this is wavelength on the x-axis and then the brightness here on the y-axis. So we could have discovered these kinds of sources, or we can discover these kinds of sources with the transient survey with Rubin. We also need some important software tools to do this. So there's this Antares event broker, which is developed at and supported at NOIRLab in the Community Science and Data Center, which is where I work. And so this is going to be a key component in dealing with this inundation of data that's going to come in when Rubin turns on. So this is kind of a new frontier in astronomy that we're dealing with, just overwhelming amounts of data, where tools like Antares are going to be super important for picking out what's interesting. So it's something to keep in mind as we kind of go forward in this era of big data and in astronomy. And then we also want to follow it up, and so we can do that with Gemini or the SOAR telescopes to classify what types of transients they are, so we know what kind of features we expect to see from these sources. And then there's this really cool instrument that's being developed for Gemini South called Scorpio, which is like the ideal instrument to follow up these transients that are going to be discovered by Rubin. Yeah, I apologize, I'm going a little quickly, but just the last couple of slides. The final point that I want to make about this project here is with JWST, that's really what we need to characterize the dust chemistry. For example, you see this feature here. This would tell us that it's silicate-rich dust. So based on the wavelength coverage of JWST, that's kind of the only thing that we would have that's able to do these follow-up studies. Now, the really fun thing about this is we're essentially already doing this. We have a JWST program, guaranteed time observation program. The PI is Mike Ressler, who's one of the MIRI instrument PIs, coordinated by myself and Jacob Jensen, who's a postdoc at Space Telescope. And we're following up transients that we discovered with Spitzer. We've already taken 2 of our 3 target of opportunities, which means what we did there is we told people, we told JWST, like, oh, go look at these objects. Like, they're pretty cool, and we want to get spectra of them. And then we observed them. So we actually got those data. And then there's another program that's coming up soon that will observe a Wolf-Rayet outburst in another galaxy. So while I can't show the spectra yet that we took in our JWST program, I can show some of these observations here. So this is looking at the part of the MIRI focal plane, or the MIRI image plane, from the imager. And here's the transient that we were looking at with JWST. And this is a target acquisition star. So in order to do spectroscopy, you need to make sure that your source is in the spectroscopic slit. And that's difficult to do if we don't know how bright exactly our source is going to be. So here's the slit. You can kind of see it here, but we want to make sure this goes in here. So we had to use this offset star to do that. And then here's another image that was taken to make sure that it's in the slit, and then you see it perfectly lined up there where we want it to be, and we got a really nice spectrum of this source. So much more exciting science to come from this, from this program. All right, so again, one of my last slides. This is not related to that source I just pointed out, but I think one of the most exciting things that we'll be able to do with Rubin and JWST and these other NOIRLab facilities or programs is to characterize the ejecta of neutron star mergers. This is showing a model here of this GW17087 merger that was discovered a couple of years ago. And we would have been able to detect it. We would have been able to characterize or to figure out if it has these spectral signatures of these heavy R process elements that are forming if we had JWST at the time. So now we just need to wait for another one of these to go off so we can follow it up and then characterize the ejecta here. So this will be a really exciting field that grows as time goes on, as we discover more of these sources with LIGO and as Rubin turns on. So to kind of just summarize this science objective, my goal in this kind of new era of infrared time domain astronomy is to get this substantial sample of all of these luminous transients and to study their dust production inputs, and to use a similar analysis like we did with the Wolf-Rayet stars, so using BPAS and comparing their dust production rates to supernovae, and then to essentially characterize and measure the dust input rates for all classes of infrared luminous stellar transients. And then, as I mentioned, there's this exciting science case of using Rubin and JWST to discover and also to characterize the enriched R process elements produced by neutron star mergers. And so all of this science is enabled by these NOIRLab programs, Rubin, Gemini, mid-scale observatories, the Community Science and Data Center, and also with JWST. And so that's the research that I'm pursuing in this kind of, with combining these synergies between these platforms to explore the explosive and dusty cosmic origins. All right, so just to summarize my entire talk, these are kind of the 3 main things that I mentioned. The first part was like the background and motivation of what's the major question that I'm studying, which is revisiting this life cycle of stars and dust. And also emphasizing why infrared time domain astronomy is the exact thing that we want to be doing to investigate these questions. I presented some of our early results with JWST that show this beautiful spectrum, direct detection of the dust emission from the Wolf-Rayet star, and also that awesome imager observation that we have. And then looking towards the future here with the combination of NOIRLab programs and JWST to do this kind of ambitious infrared transient discovery and follow-up campaign to characterize the enrichment from all these infrared luminous transients that have been unveiled in the past decade. All right, so with that, I want to thank you all for your attention, and I'll be happy to take questions.
Thank you, Ryan. We have time for some questions. We'll start with Mike.
Okay. I'm interested in slide 52.
Sure, okay. This one.
Yeah, so you talked about the instrument artifacts.
Yeah.
So I have a personal interest in removing instrument artifacts and also artifacts of computation. I was interested in the fact that you left them in. I mean, would it be possible to remove them with a decon or an overlay?
Yeah, so we thought about that, and we do have this nice looking like press image where the artifacts were removed, but I'm pretty sure that was all done with Photoshop. So to do science, or we wanted, or when we had this discussion in our call. We were like, well, it would be cool to show those images because we want to show what's real and what's not. But what I would push for in the paper was that, well, we want to show what our data look like what do the observations look like, and to make sure that we're showing, or to be as honest as possible with our observations, that we're not removing anything that we think is fake in case maybe someone else points something out, like, oh, hey, maybe this is some other artifact that we didn't think of. So in the paper, right, we left this in because we think this is better scientifically to be more honest about what our observations look like, and then to make the case that they are artifacts. So we had an image similar to this to show that the features that we see overlapping with these contours are the artifacts. So just to demonstrate, these are what the images look like. We know what's an artifact and what's not. And then if you want the pretty picture, we have the press release image to look at these dust shells. So that was our rationale. I don't think there's like a right answer to that, but that was what we're thinking when we were presenting our observations.
Thank you, Ryan, for that wonderful talk. I'm also interested in slide 52.
Oh yeah, sure.
So it kind of looks like it's asymmetric along the lower left side. Why is that? Is that like a viewing thing?
Yes, exactly. It is like a viewing thing. So if we look here, yeah, so the geometry of this like dust shell is pretty complicated. It's not like a spiral that I showed initially in the images where I introduced these types of stars. But what happens is, as this O star is whipping around in its orbit around the Wolf-Rayet star, it produces dust kind of at this region. That's where it starts, and then it continues to form dust, and it stops there, and it terminates dust production there. And we're looking at this more closely at a edge-on viewing angle than a face-on viewing angle. And so what that means is it's kind of blowing this smoke ring. So this part is going outwards towards us, and then this part here is going towards, or kind of perpendicular to our line of sight. So that's why you see this kind of like horseshoe-shaped structure, and that's kind of going in this direction here. And then there's a bottom part of it that forms here that's expanding in this direction. So it's because of the inclination where you see enhanced emission along this part of that kind of dust shell here. And because it's almost like a wine glass effect kind of thing, if you see brighter emission along the limbs or the edges of this, because you're looking at more material through this stuff here. And so that's what causes the kind of outline of, or the edges to be brighter than the other parts of this dust shell. So yeah, as I mentioned, it's kind of a complicated geometry, but we also have, this is maybe a little helpful too. So we have this figure in the paper to help visualize what the dust shell looks like. So this is what it looks like from the on-sky projection. And this thing on the right here is what it would look like if it was face on. So like here's where it would start forming dust, and then this goes out to the right, and then this bottom part goes down. So that's kind of the structure that we're looking at here. And this is, on the left is the actual observed shape of it. Yep.
This has been a great talk, thank you. Do you mind going back to the 3D printed models?
Yeah, sure. This one here.
That's really awesome. I didn't know that this was happening. But on the right, are you saying that the red is kind of that dust arc and the yellow is, what was that again?
Okay. Oh yeah. I didn't explain that too well. So yeah, this kind of like Frito shaped thing. That is where the dust forms around the Wolf-Rayet star, and then in these, like, I guess maybe bugle shaped things, they're like that's where the colliding winds are, but you don't have dust formation. So you constantly have the two stars interacting with each other. So you always have that colliding wind interface as the stars are moving and orbiting around each other. But only in this particular region is where you get that dust formation occurring. And so that's why it's red, and that's why this yellow stuff is yellow, I guess. There's no dust forming here. But the 3D printed model here is just to show what the entire structure looks like. And so, for example, if what I'm showing here is only the dust, but if we wanted to model all of that colliding wind interface, like the gas and the dust, you would see a much more spiral-like structure that appears more closely to the yellow stuff there. So yeah, that's a really good question and a good point, that this is the entire colliding wind structure that we're looking at, but not all of it forms dust. It's just this region here.
I'm going to take a follow-up on that one.
Right.
So Megan over here, who asked the last one, had a wonderful little research note about optical photometry of WR140 and how every periastron produces different amounts of occultation due to the dust in the optical. So I'm guessing it's just a geometry thing, but have our models gotten to a point where we can add enough clumpiness to account for the different types of occultations or dips or whatever you want to call them in the optical, with the beautiful, reproducible, same all the time JWST image that we see in the infrared?
Yeah, that's a good question. I don't think we're there yet with the models or with the geometric models, because there's a lot of not quite stochastic. I'm trying to remember what the optical light curve looks like. But the clumping, that's not reproduced in the geometric model. Those are all kind of just smooth structures that are being modeled. But I think that's kind of the next step to, if we're trying to understand how dust forms, do they form in clumps or do they form in these like smooth sheets of material? That's one thing that we would want to look at and of course model. I'm not sure if these geometric models can do that. These are simple geometric models, but there's other types of more complicated modeling that could be done to try to connect the light curve to the wind collision and then to the dust formation. So I don't think we're not quite there yet with these models, but I think that's like an interesting direction to take this light curve analysis and combining that with the orbit that we know, the colliding wind structure that we know, and the winds, and then the dust formation.
Ryan, we have one more student question, I think. And for any students that don't want to ask something in front of everyone else, that's okay. There are opportunities. He'll be around this afternoon, especially around my office and meeting with research students, working with Dr. Pradhan and I this afternoon. So feel free to bring your questions then as well. And after this one, let's give him a wonderful thank you again.
I'll take the thank you now too.
I just had a question about what happens to these dust formations as time progresses. Like, do they like act like nebulas? Could they form things, or do they coalesce? And also how the composition of the dust differs from the composition of the star itself.
Okay, I like that question. So, yeah, that's kind of what we're thinking next here. So, right, what happens with all this material that's formed from this? We think it likely gets piled up onto the edge of this Wolf-Rayet bubble that's blown out by the Wolf-Rayet star, which is much larger in size than what's shown here. So it would be like, yeah, it'd be way huger than this structure, this bubble. So presumably at that point, all this material will be piled up at that, I guess, interface between the Wolf-Rayet winds and the swept up interstellar medium. But yeah, the question of like, what does this look like if we go further out? That's one of the things that we were thinking of. Another observation with JWST, like what if we just take a really deep observation over here, like on the bottom right? How far do these shells go? So there's still lots of interesting things to investigate of like what happens after these shells form. Do they pile up at some point? Most likely they do. And if we looked at, say, the surrounding environments around this star, and if we're able to identify those same dust features that we see from the Wolf-Rayet star in that surrounding interstellar environment, that would help tell us that it is indeed reaching that point and solidifying that argument. For your second question, which is a really great one about the dust composition and how that relates to the composition of the star. So I think there's a reason why it's only carbon-rich Wolf-Rayet stars that seem to form dust. Only certain materials form dust in space, typically heavier metals. Like you don't really get hydrogen, like pure dust made of hydrogen. You need the right elements to form dust. So there are other types of Wolf-Rayet stars, like nitrogen-rich Wolf-Rayet stars, but those don't seem to form dust. But these carbon-rich ones do. And presumably the reason for that is because carbon it's easier to form dust with carbon. And the composition of this Wolf-Rayet star is like 40% carbon by mass. And so all of that material is going into the formation of that carbon dust. Or not all of it, but a good fraction of that material is forming the carbon that we see in the dust. But there's also lots of other elements in that Wolf-Rayet star, like sulfur, neon, oxygen, other heavier elements that the star is also producing. But those they're not quite as favorable for forming dust as carbon is. So the dust doesn't quite capture all of the elements of the Wolf-Rayet star, but it does capture carbon because of how carbon can form into these dust grains. That was a really good question.
All right, let's give Ryan a
All right, thanks everyone.